In today's video, we'll be talking about touch sensors. What is a touch sensor, or rather, what is a capacitive touch sensor, as this is going to be the kind we'll be discussing today. A capacitive touch sensor detects touch by measuring changes in capacitance when a conductive object, like a human finger, approaches or touches sensor's surface. These changes can be interpreted as input which microcontroller can use to trigger actions. You can say that a capacitive touch sensor is a kind of a capacitor. A capacitor is built with two primary components. Two conductive plates. These plates are made from a conductive material like metal. They are placed close to each other, but they do not touch. And then non-conductive material. This material is placed between the plates. Common dielectric materials include air, ceramic, plastic, glass, or paper, depending on the type of the capacitor. When a voltage is applied to a capacitor, the plates store electric charge. One plate becomes positively charged, while the other becomes negatively charged. The dielectric prevents the flow of current directly between the plates, but allows the capacitor to store energy in the form of the electric field. Now, how this construction compares to the touch sensor? We have a PCB on which we place a copper pad, creating the area where you can touch it with your finger to change the state of the sensor. We can also place a protective overlay like glass over the area. So how does this setup function as a capacitor? The copper pad on the PCB acts as one conductive plate. The PCB material, the overlay, and the air act as a dielectric. Your finger, which is a conductive object, serves as the second plate when it approaches the copper pad, forming a temporary capacitor. The sensor has some inherent capacitance, and when your finger approaches the pad, we measure additional capacitance introduced by your finger. This change can be detected and interpreted as a touch input. So let's say we detect a change in capacitance. At this point, it's not something we can directly send as output to a microcontroller. To interpret these changes and convert them into usable output, we use TTP223 chip. Now let's take a look at the pinout of this chip. It has 6 pins. Pins 2 and 5 are used to power the chip, where VSS is connected to ground and VDD is connected to 5 volts. Pin 1 is the output, which provides the signal. Pin 3 is the input, which receives the signal from the copper pad. Pin 6 determines the sensor's behavior, whether it will be active high, meaning that when we touch it, the output will be high, or active low, which sets the output signal to low when the sensor is touched. Pin 4 determines the output type. A low signal configures it to direct mode, meaning it works as a momentary switch, while a high signal sets it to toggle or self-latching mode. When you buy a touch sensor module, the configuration of pin 4 and 6 is usually predefined, so your purchased module will have the set behavior. Or does it? I will touch on this topic later in the video. In this video I will be looking at 3 types of capacitive touch sensors I found while going through my inventory. Let's begin with the first sensor. The designated touch interface is marked by a circular pad on the front, with a conductive plate located on the reverse side. The module has 3 pins, one for output, along with VCC and ground pins. You can also see the TTP223 chip mounted on the board. Now let's connect this touch sensor and check how it's configured and what the sensor behavior will be. Before I create the circuit, I like to check how the touch sensor is represented in circuit diagrams. Here is the symbol. This indicates that it's a proximity sensor, while this symbol shows that it's specifically a conductive sensor. The symbol at the bottom indicates that the sensor is momentary, on when touched. If it were self-latching, the symbol would look different, like this. To indicate whether the sensor is active high or active low, we add this symbol at the output for active high and this one for active low. I will start with a simple test using it to control a single LED without a microcontroller. For this dry run, I will use 5 volt power adapter with a DC jack screw terminal and 2 jumper wires to power the circuit. To build a circuit where a touch sensor controls an LED, the layout would look more or less like this. I have connected the touch sensor to VCC and ground. If you watch my previous videos, you are probably familiar with the LilyPad LEDs I often use. They make things easier since they come with built-in current limiting resistors. The cathode is connected to ground, while the anode is connected to the output pin of the touch sensor. Now let's power up the circuit and test it. Let's put this 3D printed shade on top the LED. When I touch the conductive surface, the LED lights up, indicating a high signal at the output when the sensor is activated. As soon as I remove my finger, the LED turns off. This means the TTP223 is configured in active high mode with a momentary non-latching behavior. Sorry for interrupting this video with this message. If you do not like this video, don't like it, do not subscribe to my channel, don't even consider becoming my patron or channel member. But if you do, maybe it's not such a bad idea. And now, back to the video. 1 touch sensor down, 2 to go. Now let's take a look at this one. This one looks completely different, featuring a glass or plastic overlay with an LED backlight. On the back you will see the same 3 pins, VCC, ground and output, but arranged in a different order. You can also spot the TTP223 chip. Let's connect this sensor in a similar fashion like we did before. Done. Now let's see how the sensor behaves. After touching the overlay plate, both the LED and sensor's backlight turn on. When I remove my finger, both remain lit, and they only turn off when I touch the sensor again. This indicates that this sensor is configured in active high mode with a self-latching behavior. Now let's move to the final touch sensor. This one is much smaller, and I ordered several of them. They arrived as a single PCB with multiple modules arranged side by side, designed to be easily broken apart. Let's break off one of these modules so we can take a closer look. As you can see, it's small enough to fit on my fingertip. You'll notice the same pins as before, but again arranged in a slightly different order. The TTP223 chip is also present here. Take a look at the size difference compared to the first module we reviewed. We'll connect this sensor just like we did with the other 2 sensors. Once a circuit is powered, we are ready to test it. As you can see, this module behaves just like the first one. When I touch the conductive surface, the LED lights up, and when I remove the finger, the LED turns off. You might be wondering why I am showing 2 sensors that look different but perform the same function. Isn't this a waste of your time and mine? Well, the reason I am showing you this module is that we can actually influence how this touch sensor behaves. If you flip the PCB over, you will notice 2 pairs of copper pads, labeled A and B. Right now, the A pads are not connected and neither are the B pads. By soldering these pads together, we can change the sensor's configuration. Let's represent connected pads as 1 and disconnected pads as 0. This gives us 4 possible combinations. 0, 0, both A and B disconnected, which is the default setting we just tested. Active high with momentary output. 0, 1, B connected, A disconnected, gives us active high self-latching output. 1, 0, A connected, B disconnected, provides an active low momentary output. 1, 1, both A and B connected, results in active low self-latching output. Now let's solder the B-pad pair to try out the self-latching configuration. I will start by soldering the header pins, but I will do them the other way around so you can see AB configuration clearly. The touch sensor should still work when we touch it from the reverse side. The first one went smoothly, but the second was a bit of a challenge, and I completely messed up the third one. Since I have used all the touch sensors I bought, I will only be able to show you the test of 2 configurations. You will have to take my word for it that the third one would work as well. I've set up 2 LEDs to test both configurations. All I need is to plug in the sensors. Here is an option 01, be connected, and finally option 11, both connected. 10 option is unfortunately missing. Let's power it up and observe how the modules behave. The first one works as expected. The second one is also functioning properly. Now you can see we have 2 self-latching touch sensors. One is active low, so when we power the circuit, the LED starts in the on state. The other is active high, meaning the LED is initially off and we need to touch the sensor to turn it on. After the first touch, both options behave in a similar way. Since this is an Arduino channel, let's finish this video by writing an Arduino sketch to use the touch sensors. Enough of controlling LEDs. Let's switch things up and use servos instead. In this setup, we have a servo powered from the breadboard's 5V and ground rails, connected to digital pin 9, and a self-latching touch sensor connected to digital pin 2. I also have a second momentary touch sensor with its signal pin not connected. Both touch sensors are active high. We will be swapping the signal jumper wire between the first and the second sensor. The goal is simple for both touch sensors. When the sensor is activated, the servo will move. Once it reaches its limits, it will reverse direction and continue moving in the opposite direction. The touch sensor works similarly to the push button. However, the key difference is that the touch sensor provides well-defined states at the output, so you don't need pull-up or pull-down resistors as you do when working with push buttons. Now let's look at the code. First, we include the servo library. Then we create a servo object and define the pins for the servo and the touch sensor. We also declare a variable angle to store the servo's current position and the direction variable where 1 represents forward movement and -1 represents reverse. In a setup function, we initialize the servo by attaching it to the specified pin, configure the touch sensor pin as an input, and move the servo to its initial position. In the loop function, we read the state of the touch sensor. If touch is detected, we either increase or decrease the servo's position based on the value of the direction variable. When the servo reaches either 0 or 180 degrees, we reverse the direction, causing the servo to start moving in the opposite direction. Finally, we update the servo's position. A 20 milliseconds delay is added at the end of each loop iteration to ensure the servo moves smoothly to the new position. Let's start with the self-latching touch sensor. When we power the circuit, the servo moves to its initial position. The servo will only start turning when we touch the sensor and its backlight turns on. It will continue rotating until we touch the sensor again, which stops it. Now let's replace the self-latching sensor with a momentary one. In this case, the servo will move only while the touch sensor is being pressed. As soon as we remove the finger, the servo will stop. YouTube suggests that to build up my user base, I need to engage with you, my audience. So here is a little challenge for you. We saw the servo's behavior with a momentary touch sensor. I made few changes to the code and will now load updated sketch. What modifications to the code would be required for the servo to respond to the touch sensor in this way? And once you have figured that out, try it again, this time using interrupts. Both sketches are available in the description below, but try to crack the code yourself. No peeking. And on that positive note, I am signing off. I will see you in my next video. Ciao.